Hello everyone, and welcome to this webinar on MapReduce Design Patterns. So this is going to be a short webinar on MapReduce Design Patterns, in which I will introduce you to this topic and also discuss a little bit about different varieties of different classes of MapReduce Design Patterns that exist. And we'll also put some emphasis on talking about the join patterns. So the objectives of this session is actually threefold. We have to look at the why, who, and what of design patterns. As far as the why is concerned, what we'll have a look at is, in this whole course, we will be discussing a lot of different varieties of design patterns. And that's what we want to have a look at when we talk about why people programming in Java or people who are involved on Hadoop need to understand the design patterns. So that's what the why is about. Then we'll move on to talking about who should be interested in learning about MapReduce design patterns. So we'll have a short discussion on that. And then we'll move on to discussing the what of the design patterns, where I will introduce you to different varieties of design patterns, different classes of that. And then we'll have a little bit of a detailed look at the join patterns, where we'll also have a look at one of the examples of one class of design patterns, which is called the reduced side join patterns. So the question is why we require the design patterns. So people who have traditionally solved problems on traditional systems, for example, have a look at, for example, a sorting algorithm, right? So there is a quick sort algorithm which you can use to sort your data, and you have done that for, people have done that for ages. Now, can you just take the same algorithm that you have for quicksort and apply that to a MapReduce framework, kind of a parallel system? The answer is no, it's not possible to do that. And why it's not possible? It's not possible because there are certain constraints. When you start programming for a framework, there are certain constraints that you'll have to adhere to. And then, of course, frameworks also provide facilities for you to do programming in, to be able to program to that kind of a structure. But then there are certain constraints also. Now, to be able to exactly fit the way you have had your programs executed earlier in a traditional system, you'll find it very difficult to implement it similarly on a system like a MapReduce framework. And one of the reasons is, for example, I talked about a constraint. So one of the constraints is your mappers, right? So your mappers cannot talk to each other. Now, whenever you supply a data to your program, so for example, a single MR job, that data is split, right? You have multiple splits. If the data size is really huge, then that stuff is going to be split across different input splits. And different map tasks are going to be handling that input split. Now, there's no way for these map tasks to communicate across each other. And the only way and the only point at which these things get to, this data actually comes together to a certain extent is at the stage where you are doing sorting and shuffling of the data. So that's a constraint, because if you look at a quicksort algorithm, what you're basically doing is you are doing a recursion over your set of data, and you're basically dividing the data set. And then when you reach a terminating condition, after that you combine the data set. So one of the major requirements there is that you need to be able to communicate across different threads of execution that they have. And that's not possible when you're dealing in a system like MapReduce. Okay. So that being the case, because you cannot apply that algorithm directly to this, and there are multiple cases of this, and I just gave you one of those examples. I can give you multiple other examples. For example, look at graph algorithms. So graph algorithms are mostly iterative in nature. And if you want to execute the algorithms that you have as it is, for example, talk about shortest path algorithm, if you want to execute that stuff directly as it is on a MapReduce system, you will find it very tough. Because graph algorithms are basically iterative in nature, and MapReduce programs, by their very nature, it's one shot, right? You have your data, you give it to your mappers. Actually, before that, you have your input format, which actually reads all this data and divides it into input split, and then your mappers execute that stuff. And then there's a shorten and shuffle phase, there's a partitioning, shortening in the shuffling phase, and then you have the reducers running, and then you have the output coming out. So basically, it's in the whole MR job is one shot. There's no iteration in that. Now, for you to be able to implement a graph algorithm on this kind of a system, you will have to learn different ways of doing it. Okay, so I have given you two different examples so far, where the way you have solved those problems earlier cannot be applied, those algorithms cannot be applied directly to this system as it is. So that warrants you to understand how this system actually works. And you guys definitely know about it. Anybody who had experience, a little bit of experience with Hadoop knows a little bit about it, but being able to program it properly, that's where the role of the design patterns come into picture. So to be able to solve a problem in a certain way, there are people who have tried to solve that stuff in similar ways over the years, and they have figured out that this is the best way to solve this. And that's where, as I said, the role of the design patterns comes into picture. So if you, it will reduce your time to development. You will see, when you are looking at a complex problem, you'll see these patterns occurring in different places. Actually, in a huge system, huge big data system, what you will see is a multiple of these patterns that we'll talk about will come together to solve the whole problem. So that's the idea of the design patterns. So it's good to use the way people have solved these problems over the years, and if you do that in similar ways, you'll see that the development time actually speeds up, and also the quality of the program that you will have will definitely be better. So now, having discussed why you require to know a little bit about the design patterns, on this slide, let's have a short discussion as to who are the right audiences for this. So a Java developer who wants to get involved into writing programs in the big data world. Okay, so because the stuff that I'm talking about right now is actually dealing with Java MapReduce. So Java programmers can learn to program on this parallel system by learning about some of these patterns that we discussed as part of this course. And then it's not only for the beginners, somebody who has been programming in MapReduce for some time, or somebody who has had a preliminary course in Hadoop and knows about different components of this, and maybe somebody who has already been programming in a pig kind of a language. Those people can also learn about the design patterns to be able to increase their expertise and be better programmers as far as MapReduce is concerned. And if you want to be a Hadoop architect, then I would say that this is definitely required because MapReduce is one of the integral parts of Hadoop. And anything which gets implemented, for example, even if you're programming at a slightly higher level, for example, at pig and hive levels, ultimately those programs get converted into MapReduce. So anything which you end up dealing, which is complex in pig also, to be able to be a good programmer, it's good that you understand how things actually happen in the background. So overall, anybody who is involved with the Hadoop ecosystem should have a certain understanding about MapReduce design patterns, which helps you if at whatever level you're trying to do programming on these systems, will help you be a better programming at those levels. That was some of the introduction to the who and the whys of the MapReduce design patterns. After this, we'll start getting into the what of design pattern. And on this slide, I will talk about different varieties of patterns which we discussed in this MapReduce design patterns course. Basically, we discussed 7 different varieties of patterns in this course, and 6 of these are listed on this slide here. The 7th one actually is a graph patterns, which is also quite a prominent part of this course. And one of the things that you'll see when you move from one of these patterns to things which happen on the other spectrum, the complexity of these patterns actually tend to increase. So on one end you have patterns like summarization, which has to do more with a high-level summarization of the data. So before you go ahead and do any analytics on the data that you have, the first thing that you do is try to understand and get a high-level view of the data. And that could be either on numeric data, or that could be also on text data. So if you're talking about numeric data, some of the things that we'll end up doing is you'll probably find sums of that data, you will find minimum, maximum, median, those kind of things you will find, standard deviation, variance. And once you understand by using some of these summarization patterns, once you have an initial understanding of the data, then you can go ahead and do their further analytics down the line that you have in the pipeline. Much more specific things you can concentrate on. So that's where the role of summarization patterns comes into picture. As far as summarization patterns is concerned, as I said, there's certain of these patterns which deal completely with the numeric data, and that's the example that I gave you just now. But there's other type of summarization patterns which deals completely with the text data, and one of those patterns is inverted index pattern. So what happens in inverted index is you have multiple text files, and then one of the things you could be doing is you are building an index, which is a data structure from the terms that you have in your document to the places where those documents actually occur. Now this is something which is used quite frequently in the Google search engine, where what they do is for being able to provide information retrieval in a much quicker way, there is this index which is maintained as far as the text data is concerned. So these things are first of all, the crawling of the web happens, and after that, based on that crawl, the indexing of that data is done. And so indexing pattern is one of the patterns which can be used to create inverted indexes. And because these patterns that we're talking about actually deal with big data, so you can actually create indexes on internet scale data using the patterns which will be talked here. We'll also go on to talk a little bit about some of the features which the MapReduce framework itself provides. So we'll talk about something called counting with counters as part of the summarization pattern. So that's about the summarization patterns. One of the things which you should notice when talking about summarization patterns is they make changes to the data to a certain extent. So whatever is presented to you after these patterns are run, that data is slightly different from what you had started with. Then there is another set of patterns which is called the filtering patterns. And filtering patterns, as the name suggests, is a pattern where you actually are trying to take subsets of your big data. And that's again for the purpose of concentrating on a subset which is of more interest to you. Okay, and so summarization was also about, first of all, having a higher level view of the data. And then after that, once you have understood the data a little bit, then you try to look further down in the data, try to understand more about it. Filtering is trying to focus more on certain subsets which are of more interest to you. That's what filtering pattern is about. And in this, we'll talk about 4 different varieties of patterns, and generally we discussed initially talking about some of the basic patterns, which is there in filtering, and then we move on to talking about something called Bloom filters. A Bloom filter is something which is quite useful for big data kind of data sets, because it's a kind of a filter where which takes very little amount of storage to store, and this we won't be putting too much of emphasis on Bloom filters itself in today's webinar as such, but then just keep in mind that that's one variety of patterns which is quite prominent, and it's quite important from the big data perspective. Then we talk about a couple of other patterns, which is the top 10 and distinct patterns. Generally on traditional system, the way you would solve your problems related to top 10 is you'll just go ahead and sort your data first, and then you'll take the top 10 out of it. But because sorting is sort of an expensive operation to perform on MapReduce framework, so considering that, we have a different way of solving the top 10 problem, and so that's what we discussed over there. We'll also talk about another pattern which is called distinct pattern, which is useful for removing duplicates from your data. Now, people who have been involved in CRM would know that there's a whole lot of data related to customers which is actually duplicates, and one of the things which people have to do before they do further analytics on the data is to make sure that a lot of those duplicates are removed. So for any high fidelity analytics, you will have to remove the duplicates from the data. Then there is another set of patterns which is called the data organization patterns, and these patterns are more about reformatting your data from the current state in which it is. And in this, there are different varieties of patterns. So there's a couple of varieties of patterns which deal with partitioning of the data. So one is called the partitioning, the other is called is bidding, but both of these actually deal with partitioning of your data. And then there's a couple of patterns which deal with sorting of the data. So there's a total order sort, which is also called the global sorting. And then you have secondary sorting. And these two have nuances and usefulness of their own. So we discuss these patterns as part of that module. Then there's another set of patterns which is called the meta patterns. So all the patterns which you just saw, and actually that also includes a join pattern, on which we'll put some emphasis in our lecture today. So join pattern, again, there are different varieties of that. There's certain patterns which are completely on the reduce side, and then there are certain patterns which happen completely on the map side. There are say different nuances to these, and there are certain benefits to using things completely on the map side, because if you do things completely on the map side, your performance of your job actually improves, because you don't have to be bothered about transferring your data across the network from mappers to the reducers. So there's this saving of the time when you do the network I/O and the disk I/O. And actually there is some empirical data which says that almost 30% of the time the MapReduce jobs actually transferring data across the network. And actually people these days are looking at SDN, actually there's something called software defined networks, to be able to provision the network bandwidth properly depending on when the data is required for your MapReduce job. So that's one of the applications of something called software defined networks in big data. Okay, so I just deviated a little bit from the topic. So we also talk about join pattern, as I said. When you move completely from doing things on the reduce side to map side, you end up losing some of the flexibility that you have with doing things completely on the reduce side. And we'll discuss that in the slides that I come to after this. All right, so now quickly talking about the meta patterns. So meta pattern and the input-output pattern are slightly different for all the other patterns that I just talked about on this page. The difference being that the confines of all the previous 4 patterns I talked about is limited to a single MapReduce job, whereas the confines in meta patterns goes beyond a single MapReduce job. But actually, meta pattern is not a pattern in real sense, because you're not trying to solve a business problem here. You're basically trying to chain together multiple MapReduce job in a directed acyclic graph, so that you can build more complex system out of your MapReduce jobs. And then there is another one which is not listed on this page. That's called the graph patterns. And we discuss 3 different varieties of graph patterns. We start with talking about the shortest path algorithm. And then we talk about the friend of the friend algorithm. That's something which is used by Facebook and Google for suggesting potential friends to you. And then we talk about the page rank algorithm, which is used by Google to rank their pages when they show you pages when you search for something. We talk about the input and the output pattern. So this is slightly different from other patterns in the sense that most of the other patterns that we're talking about on this slide deals with reading and writing from HDFS. But as far as the input-output pattern is concerned, they facilitate reading and writing directly from an external source. So you could either be reading from maybe a web service through REST APIs, or you could be reading from a database, for example, HBase. And then you could also be doing similar things as far as the writing side is concerned. So here you're avoiding writing anything to HDFS. You're actually pushing things. If your ultimate destination for your data is going to be HBase, for example, then you can write directly from your MapReduce jobs into those. And the input-output patterns are some things which deal with it. Okay, so that was a quick summary of the different patterns which are available in MapReduce. And now the rest of the lecture is going to focus on the join patterns, and we'll show you an example of join pattern after that. Before I get into that, let me see if you have any questions, and I'll try to answer some of those quickly. Okay, so the first one was not able to hear, but I guess by this time you're definitely able to hear me. The second question is how much Java I need to learn to go with MapReduce. So because this course is about Java MapReduce, you definitely need to know the basics of Java. You can definitely learn the whole language later, but you need to have some understanding so that you can understand the examples that they show you as part of the MapReduce examples which are discussed as part of the course. So it would be good if you're able to, if you have some understanding of Java. But then because when I come to those examples, I'll also explain these whatever is written in the code. So that should definitely help, but a little bit of understanding will definitely help you in going ahead. The other one is, but Hive and pick queries not allow users to understand how the joining happened at the backend. Okay, so I see an answer there. Yes, only MR gives you full control of your operation. That's true. The other question was, is there any good reference for doing MapReduce in Python? I can tell you about some of those maybe at a later stage. Okay, so other question was, you mentioned soft design defined networks when talking about join patterns. Could you please throw some light on that? So, so the reason I mentioned that was not exactly anything related to the join pattern, because I was talking about transferring a lot of data across your map and reduce jobs. So that's in your clusters, a lot of data is getting transferred. So I had brought in this point about the software defined networks because one of the use cases one of the good use cases of software-defined networks is turning out to be big data as well. So using software-defined networks, you can actually provision the network bandwidth in certain ways that some of your jobs actually run faster. Because as I said, one of the empirical studies says that 30% of the time your MR jobs is spending in doing network transfers. Okay, now I'll move on to, there are more questions coming in, but we'll keep it for the end, otherwise we won't be able to finish a lot of stuff. Let's move on. So join patterns, basically this is something which is not new as such for any of you who has worked in the RDMS world as well. So joins happen all the time. So you have relation tables, and on the foreign key the joins are happening. But when you're talking about a scale which is big data, when you're trying to do these joins in real time, the joins can actually get, it can actually end up taking a lot of time. It actually get very costly. So one of the things you can do is join this data upfront. And most of your data actually lies in silos. So when you join these things together, the value of the operations and analytics that you can do on a joint set of data, and the knowledge that you can derive from doing analytics on that data is actually much more higher than just having those data in your silos. So that's where the usefulness of join patterns comes into picture. In this course, the data set which we use for our purposes is actually the Stack Overflow data set. And one of the examples there could be joining the comments and the posts on user ID. So they have got a table which is called posts field, which contains all the questions and the answers which users have given a Stack Overflow. That is all contained in posts. And then there's another set of data which is called the comments data, which contains some of the comments which are put forth on Stack Overflow on some of the posts which the users have described there. So we use those data, and one of the things which, as far as join pattern is concerned, you could do is on the user ID as a foreign key, we'll combine the comments and the posts all together. So you'll have the questions and the answers and the comments after that. All right. So with that, let's have a brief discussion as to what kind of join patterns we have. So the first two that you see on the slide, the reduced side join, which is also called the repartition join, and then you have reduced side join with Bloom filter. Although there's something mentioned with Bloom filter over here, but remember both these joins are completely happening on the reduced side. The only difference between the first and the second one is that before doing the join on the reduced side, on the map side we use a Bloom filter to filter out certain records which is not of interest to us, to save our time in terms of the transfer that we have to do across the network. So if we have, for example, a terabyte of data, then maybe what we can do is, if our interest is only in records which is of size maybe about hundreds of GBs, then we could do some of this filtering out on the mapper side itself with the Bloom filter. And if you do that, then the amount of data that will transfer across the network reduces a lot. So the performance of your reduced side join will definitely increase in such cases. One benefit of using reduced side join is that there are different varieties of joins. There are inner joins, there are outer joins, left outer join, right outer join, and full outer joins. Then you have anti-joins. Now, using reduced side, you can perform all different varieties of joins. But after that, when we discuss about the map side joins, and replicated join is one of the cases of replicated join, and also a composite join is something which happens completely on the map side, you end up losing, although in terms of the processing, your time is definitely going to get benefited, because you're not transferring data across the network. Everything is happening on the map side only. But in replicated join, the first flexibility you lose is your data. So you won't be able to use, whereas in reduced side join, you could have multiple large data sets, and then you could join them together. But in replicated join, it's only possible for you to do one large data set, and rest of your data sets will have to be small. And as far as the reasons for that is concerned, those things we discuss in the lectures, because that's slightly elaborate, not enough time for us to do that here. And in replicated join, you also lose some flexibility in terms of the kind of joins you can perform. So in replicated join, you can only perform two different kinds of joins, which is the inner join and the left outer join. Rest of the things cannot be done. And there are well-defined reasons for that. Then we talk about composite join. Here we use a class which is provided by the MapReduce framework itself. It's called the composite input format. To be able to join two different large data sets together. Although all this stuff is happening completely on the map side, but we are able to do this map side join on large data sets. That is not a single large data set, which is what you will be able to do with a replicated join. But with composite joins, you can have maybe multiple large data sets, maybe 10 of these, 15, 20 of these, and you could join them together using composite input format. And in the end, we talk about the Cartesian product, and this is a kind of M cross N kind of a join, where if you have M records in the left table and in the right, you actually combine each of these records with everything in the table on the right, and that's how you do Cartesian product. But keep in mind that it's very intensive in terms of the time that you have to spend. So you have to be careful when you use Cartesian products. But there are cases where you cannot avoid Cartesian product, and especially because all the other joins that we discussed on this slide have to be joined on a certain foreign key. Whereas in Cartesian product, you don't actually require a foreign key. You combine everything with everything. All right, so this slide is a quick refresher about the inner join, the outer join, and different varieties of that. So as far as inner join itself is concerned, what happens in inner joins is you have table A on the left, table B on the right, and then there is a foreign key. You combine only the records from A and B where there's a match for the foreign key. The rest of the things are discarded. So it's sort of an intersection between table A and table B based on that field, which is a foreign key in our case. Talking about outer join, so let's see, one of the varieties is called the left outer join. So what happens in left outer join is you have a left table, table A, table B. So you pick up all the records from table A which have got a foreign key match in table B. Those records are picked up. This is similar to what you do in inner join. But in addition to that, there's another set of records which you end up picking up in left outer join, and that's all the other records which happen to be in table A but did not have a corresponding record match in table B. You end up picking up all this stuff as well. So basically everything which is there in table A is picked up, and wherever there is a match, those records are combined, and for rest of the records for which there was no match in table B, you fill those stuff with nulls. And right outer join is again a replica of the left outer join. So here you have again the inner join happening first, and then after that everything which you have, any record which you had in table B which didn't find a match in table A, those things are also combined. But as far as the values are concerned from table B, they are filled with nulls. Full outer join is a sort of a combination of the inner join, left outer join, and right outer join. So what you do is everything which has got a match as far as the foreign key is concerned, those records are picked up. And then all the records from table A which didn't have a match in table B, those things are picked up, and of course filling up null values for table B. And then again the outer join stuff where everything from the right hand side of the table is picked up which didn't find a match in table A, but those values are filled up with nulls. So that's what full outer join is. Then there's another variety which is called anti-join. And anti-join, as the name suggests, is a sort of an anti of join. And the join, by its very connotation, generally refers to inner joins. So anti-join is from full outer join, you take out the inner joins, and whatever you're left with, that's actually called the anti-join. And then Cartesian product, we had a quick discussion on the previous page on that. So let's move forward. Okay, so the rest of the session today, I'm going to discuss about the reduced side join. And as I said, it's easy to implement, but it's probably going to take you longest to execute the reduced side join. So in cases where, for example, if you're trying to combine two data sets together, where one data set is small and the other data set is large, maybe you should avoid doing a reduced side join and just keeping on something which happens completely on the map side. So a replicated join would probably be better over there. So let's see. Yeah. So because you are transferring the whole data across the network, that's why the performance of the reduced side join is always going to take a hit if your data set is large, and also along with that you have many number of data sets. So multiple data sets you have. So instead of having a couple of those data sets getting joined, probably you have got 20 of those getting joined together. That being the case, you will also have to be very careful in terms of the number of reducers you use on the reduce side, because it's not only about one large data set that you're dealing with. The whole thing is getting combined in reducers, and each of these reducers will actually be dealing with all those data sets that you have. So if you're dealing with 10, 20 of these, then the reducer will have that burden of being able to handle those 20 data sets together. So you'll have to make sure that you have enough number of reducers. So joins are actually one of the most expensive operations to do on MapReduce. But the benefit of using reduced side join is that you they end up supporting all different varieties of operations that I talked about on the other side. So you have inner joins, all varieties of outer joins, anti-joins, everything can be done on that. And here's the structure for the reduced side join. So let's understand this, how the whole operation happens. So on this diagram, we are combining two different data sets together, data set A and data set B. This got 3 different input splits. Data set B has 2 input splits, and these 2 data sets are different types. So for example, the example which I'll show you will deal with posts and post links. So just assume that these are 2 different data sets. Okay, so what you do in join mapper is the mappers will emit keys as the foreign key. So there has to be a foreign key on which you will combine these 2 data sets together. So data set A and data set B are going to combine on a foreign key. In this case, it happens to be the first name in this example over here, the first name of the person. So what these mappers are supposed to do is, as key, they will emit the first name of the person, and then the value can be anything. Value can be the whole record. Any payload that you want to assign to this, you can do that. But if you want to do certain things with your join data, where you don't require all the fields, then it's a good idea to do a projection here in the mapper itself, so that you end up transferring only the fields across this network to the reduced side, which is of requirement to you. You don't transfer other superfluous things, and that will help in improving some of the performance times, which degrades quite a lot for reduced side joins. So as I said, so here is the foreign key is the key, and the value is any payload, and then you transfer that across. And while transferring that, you also append these values with some kind of a letter which tends to identify which data set this is coming from. So in this case, probably in front of MD, you will have A appended, and in this data set B, probably you will append B in front of 37. So that, and this is the logic which is followed inside the reducers. So reducers use that prefix which had been assigned based on where that key value pair is coming from to be able to make a judgment call later on. And we'll see that part in the code when I show you that. So as far as the mappers are concerned, I have already talked about that. As far as combiner is concerned, the benefit of combiners you don't get at all in reduce side join, because any data that you have on the map side, everything needs to be transferred as it is to the reducers. So there's no real benefit of using the combiners. Of course, as far as partitioners are concerned, you can use custom partitioners if you have some idea upfront that the data that you have is slightly askew. So if you use custom partitioners, you would be able to distribute that workload across the reducers in more evenly and uniform way. So in some cases, the custom partitioners could be useful. And the reducer is based on logic. I'll show you more about that in the code when I show that to you. In terms of resemblances, so you have resemblances in SQL, you have a resemblance in pig. In SQL, there's a join statement. So you say select the fields that you want to from users, and then you specify what kind of join you're doing, inner, left, right, join, and then you specify the second table with which you're trying to do the joins. And then you have again the join commands in pig as well. So you see join comments by user ID and users by user ID. So you're combining users and comments here. And then they have something for the outer join as well, where again you specify the left outer, right outer, or the full outer using the join command. Again, so what you have to keep in mind is, although these statements look much simpler, when I show you the code, that's a bloated form of this, whatever happens in the background. But that code will give you an understanding as to what's happening in the background. Although this line is looking a single line code here, but behind the scenes, a lot of things are happening. It's good to have an understanding of that. So just by having the single line, it doesn't really improve the performance on pig. It's also going to take the same amount of time, which is there on MapReduce. Okay, as far as the performance is concerned, again, I said use enough number of reducers, transfer all the data which you required on the reducer side, so use projections. And if you can use any other map side pattern, if it's possible for you to use it looking at the kind of data that you have, then use something from the map side itself rather than using reduce side. All right, so that brings us to some of the use cases. I've just mentioned a couple of them here, but in your own working environment, you will come across too many use cases of joins. And in all those cases, this is applicable. So one of the use cases could be joining the tweets with the user personal information for behavior analysis. This is something called, this is done in the CRMs. So and marketing team uses this quite frequently. So they have internal data in the CRMs, in their RDBMS. Now they want to combine this data with the Twitter handles of some of those users so that they can understand that user in a more behavioral way, the way they do tweets and whatever they're doing on those social platforms. So joining is one of the ways to combine these data together and getting more knowledge out of that combined data. And the example, this is the second one, is about the example which I will show you. So there is something called post links file and there's posts file in Stack Overflow data. And post is where, as I said, you have your answers and the questions. And in post links are basically about records where you show that this particular post has got a reference to some other posts. in a Stack Overflow, or this particular post has got a duplicate. So probably this is a duplicate of some other post. So that kind of data is maintained inside post links, and posts is where, as I said, you have all your posts maintained. So our job here is to combine all these things together into single records, and I'll show you the code for that. Okay, so here is what I just discussed in terms of the problem on previous slide. What we'll do is we'll use a class called multiple inputs class for reading from two different varieties of data. Because remember, we need to distinguish these data sets. So one of the ways, generally what we do is you have one directory in which you push all your files, and then when you start executing the program, the input format creates input splits. But you need to be able to distinguish, in our case, across these different data files. So we'll use, for simplicity, we're going to use a class called multiple inputs class. So in multiple inputs, what you do is you provide the source, you provide the mapper, which is supposed to operate on that data set, and then it takes care of doing the things for you. All right, so now let me go to giving you a quick code walkthrough of this particular example. So here is the first line, which is your command line, where we specify the reduce side join post. This is the location of the post. You have the post links location, and then you have the output directory. And then we can specify any of these as our type of join. You could say inner, left outer, right outer, full outer, or entire join. It is part of the code. So this is the driver code. If I didn't mention this to you earlier, so it's good to start by looking at the driver code first, because that sort of is a place from everything starts. So that works as a framework for you to understand the whole program much easier. All right. So in this part, we are just checking whether the value for the type of join which is passed in is a valid one or not. Some of the code in here is boilerplate. So if you have dealt with MapReduce code earlier, you know about it. So here we are creating a job, an instance of the job. And then some of the configuration is being done here. So in that job, we are configuring that job with the type of the join we need to perform, because that's something which needs to be passed to the reducers, and they will read it from the configuration. And then here is the class which I was talking to you about on that slide. So here's a multiple inputs class on which you call add input path. And then to that, you have to specify the source location. So in our case, the first location was the post location. So that's what is being provided over here. And then have a look at this mapper. So what we're doing is for these two different varieties of sources that we're dealing with, we're using two different mappers. Because when you have different varieties of sources, the kind of things that you have to do with that data might be very different. So you need to implement different mappers for all those multiple inputs that you have. And then we set the reducer class here. And that's the rest of the things are pretty much boilerplate. It's used in all the programs that you have on MapReduce. Okay, now let's go and see what's happening in the mapper. So the first one is a post join mapper. What you do is we are going to do a join on the user ID. So that's a field we're interested in. This first thing that you're seeing over here, it's what it's doing is all that data is kept in an XML file. So the post data is an XML file. So this utility is reading from that XML and it's filling up a map. Okay, so this is called the parsed map. And there are, in each of the records in post, there are multiple fields with values. So it reads each of those lines of records, and parsed is then filled up with the key and the value. All right, so once that is filled up, we get the user ID from that, which is here, the post ID. And then we check whether it's null or not. If it's null, we just skip that. We return from that call to map. And then here we are setting the out key as the post ID. Sorry, so initially I probably mentioned we are using the user ID. We're not using the user ID, we're actually using the post ID. And then we are setting the value here. Remember I had said we are using the same value. We are using the full record here, which has been passed in here. But we are prepending that with P to identify that as coming from the posts. And then we just write that stuff out in context write. So we have the out key and the out value being written out. So that was the first mapper. Here's the second mapper. It also does similar things to a certain extent. The only thing is that foreign key within post links is mentioned at post ID. So we read that field as post ID. And then we set that post ID as the key. But just keep in mind that this post ID here and the ID we saw in the previous mapper are the same foreign keys. And then as far as the value is concerned, we are prepending that value with L, and then everything is getting written out. And then what we do in the reducer, that's pay attention to this part here, because that's important. What do in so before this reduce method will be called, the setup is going to be called for this reducer. And the join type is mentioned. As I said, that was being set in the configuration over there, so that join type is being read in the setup method. All right, so get into reduce. So inside reduce, remember, you have this key here. So this key is going to be a foreign key. And for that foreign key, all the records which pertain to that foreign key across different data sources that you had will be part of these values here. Okay. What we do inside the reducer is we maintain two different lists. We maintain a list for the posts, another list for post links. And in this for loop, we are not doing much. Basically, what we're doing is we are reading all the values for that foreign key, and we are separating that out again based on whether that came from post or that came from post links into list posts or list post links. All right, so that was what is happening here in the for loop here. And then the whole magic of doing the joining happens inside this method, which is called execute join logic. And this executes based on the kind of join you have asked this method to perform. So let's maybe look at a couple of these. So I'll have a look at the inner join. First thing that we check is the type. So here is, if it's inner join, then look at this condition here. We are testing whether any of these is list is empty. So is the post list link empty or the list post empty? Now remember, inner join is more about the intersection of the two tables based on a foreign key. Now if any of these list is empty, then basically the intersection is null. So that's what is check over here. So we want to make sure before getting into any of this logic of combining, joining, we want to make sure that none of that list is empty. All right, so now we have made sure if we get into this, we have made sure that these lists are not empty. Then your job is just to combine them together. That's what we do in these nested for loops here. So you read from list posts and then combine each of those records with everything inside the list post links. That's it. Remember, at this point in time when this method is called, we are talking about all the records only for a single foreign key. There would be multiple of those such calls to reduce, and this will be called for each of those keys. Then let's look at one more of these examples. Let's do with the left outer join. Let's see. So as I said, in left outer join, we read everything which is there in the left table, and that's what we do here. So we read each record from the list post, and then we do a couple of checks. The first check is whether the list post links is empty or not. If that is empty, then sorry, this is a case where it's not empty. So that's the place where you just go ahead and combine. So this was sort of the inner join case for left outer join. And then you have the other case here where you just output everything. Even if there was no match, you get into else, there was no match, but you write everything out. That's what is being done here. You write all the records from A, and as far as the write value is concerned, you just append no values to that. So write outer is pretty much of similar variety, and I'll just skip the other ones and move to showing you a run for this. Okay, so just have a look at this command line. So we have the reduce side join post. That's the name of the class that we're dealing with. And the first input that you see here is the post.xml is contained inside this. The second input is post links. And then this is the output directory where everything is going to go out, and we are doing a left outer join here. So let's run this. Okay, our data set is not very huge over here, although the data set stack of data float is really huge. When I had downloaded that stuff, a data set from January to September in 2014 was almost, after unpacking that stuff, was almost 138 GB. So we cannot deal with that huge data sets on a laptop in sessions which are smaller. So we have truncated data sets, so these things run quite quickly. Let's see the output. So let's move a little. Look at the input paths here. So because we had used multiple input paths, and there were two paths to process. That's why I see two paths, and you had two splits. Let's have a look at the output. Okay, so what's this showing you now is these are the combined records from the post and the post links after joining them together. Okay, it's I say it takes a bit of time to do the joining, even on that smaller data set. All right, so that's it. You see some of these rows here getting combined. All right, so that was a short and quick example of one of the join patterns. And we discussed multiple varieties of this whole thing in our course. So let's see. All right, so with that, so in terms of the content for this webinar, I'm done. Let's see if you have any questions. What is the advantage of using MapReduce joins over SQL? No, so we are not talking about SQL here. I was just trying to give you some analogy with some people who are coming from the SQL background. So just trying to give you an analogy. So there's nothing nothing with respect to MapReduce itself, joins, that I wanted to emphasize over there. So SQL and that's for RDMS data sets. MapReduce is for the big data. So there's no advantage as such, because I'm not trying to talk about one being better over the other over here. I'm just trying to give an analogy over there. Can we get the video recorded session of this session? Probably you should be able to have that. I'll have to check that with the support folks. We're using 0, 1, wait for completion true. Yes. So that's actually a blocking call over there. There are different ways of submitting your jobs to the MapReduce framework. So one of the ways is wait for completion, where you submit it and you actually wait for it to complete. The other way is submit job, where you actually give it to the system and then you come out of it. It's not a blocking call, and then you later on you can check for whether the job completed or not. Oh, that was only checking for certain conditions over there, some exit conditions. So that's actually coming from a different place. The 3 that was there was coming from a different place. Can we get the code for this? Yeah, so this code is part of the lectures that we have as part of the MapReduce Design Patterns course. It's part of that course. Can you please show the input files? Okay, please send the program. Coming to the next one, which is about the script to run that program. So because this is not too complex, everything I did was on the command line. So this was just using the Hadoop command and the jar files and specifying the class, and then the inputs and the outputs. So we didn't have any script for doing this. Are there any good books, resources to follow in this topic domain? Yes, there is a very definitive book on MapReduce Design Patterns. So if you search on the web, you'll find that. Could you share the Java MR code? All this stuff is going to be in the LMS. It's already present in LMS. So if you have access to that, so you can definitely have a look at that. Please show us both input data files once. Okay. I'll just quickly show you that. Can the design pattern be extended to Spark, Hawk? Yes. So the thing is, it can the patterns that I talked about can be extended, but the programs and the example that are shown to you would not work as it is. So Spark itself has got a framework of its own. You will have to write it in that way. But as far as the design pattern is concerned, yes, that can actually be extended. Okay, so I'm just trying to quickly browse through some of the other questions that you have. Some of those, I guess, has been answered as well in between. Let's see. Joins are much easier to perform through Apache Crunch than in Hadoop. I'm not familiar with Crunch, but because this course is about MapReduce design patterns, so it was talked in that respect. It might be easier to perform over there. Actually, I just showed you the pig code as well, so that was just a single line of stuff for you to do. So the idea is to show you the complexities behind it, for you to understand it, what's happening in the background. And for people who program actually on Java MapReduce, for them this is completely required. As a design patterns, okay, so these questions I guess I've already had a look at. Okay, so recorded session will get, there should be a recorded version of this that should be on LMS, I guess. Should check with the support folks. Will we need to have Hadoop cluster to take this course? No, so as I said, we have truncated our examples in terms of the data set. So although those examples can run on larger data sets, but as far as this is concerned, this course, we can do this stuff on our laptops. Machine configuration for Hadoop, you will get those things as part of our course material, which is there on the link over here, MapReduce Design Patterns. Just go to Edureka site, check for MapReduce Design Patterns. There is some material on that as far as what is the machine configuration to be used for this. We have videos from Edureka for MapReduce Design Pattern. What areas are covered in depth in the course apart from the uploaded videos? So there was a slide in the lecture where I had shown you different varieties of design patterns. So each of these design patterns have different types inside them. So we talk each of those in details, and we give examples of each of those as part of the course. And one of the things to keep in mind is those patterns, when you start and you reach the other spectrum of that stuff, for example, starting with summarization patterns and going to graph patterns, the complexity will increase substantially. So that's all what is covered in the course. So the multiple varieties of patterns would be covered. So any other question? Okay, so I missed showing those input data files. Let me get to that. I'm just opening some of those files. I'll show you what I'll do is I'll show you the top 5 or 6 records from those files. So here is how these files look like. So you have these records, and this is from the post.xml, and I'll show you for post links. Yeah. So the other data is from post links. No, this is for reading these XML files. There is a simple utility to do that, and what we do is we read each of these records one by one, because that's what is forwarded to us by when you call the map. Each of those records is a single line, and that's what comes in, and then we call that method, which is there, that utility, small utility, and what we do is we just read all those fields and the values into our map, and then use it for our purpose. There would be a lot of other ways of reading the input, but we use it for this. This is the way we actually use a text input format for doing it. Okay, so I hope you guys found it useful, and it was nice interacting with you guys. Thank you. If you don't have any questions, we'll call it a wrap, and thanks for attending. Goodbye.